Calgary Framework 20 is a leading candidate for use in CO2 capture from humid flue gases and from humid natural gas. An important feature of CO2 water adsorption in CAF20 is the prevalence of strong thermodynamic non-idealities. In order to demonstrate this, I plot the experimental data of Rajendran and co-workers published in Chemical Archives 2024 as a function of the percentage relative humidity. The blue triangles are the component loadings for water, and the red circles are the component loadings for CO2. These experimental data are determined from breakthrough experiments. There are significant deviations of the experimental data for CO2 and water loadings from the IAST estimates that are indicated by the dashed lines. In order to quantify the mixture adsorption equilibrium, we need to adopt an appropriate model to describe the activity coefficients in the adsorbed phase. I use here the NRTL model for the activity coefficients. This plots the Gibbs excess free energy as a function of mole fraction in the adsorbed phase, and the red symbols are the experimental data points, and the continuous black line represents the NRTL model. A special feature of the experimental data is the existence of two different regimes. For percentage relative humidities lower than about 50%, the adsorbed phase is richer in CO2, i.e. poorer in water than the estimates of the IAST. On the other hand, for percentage relative humidities in excess of 60%, the adsorbed phase is poorer in CO2, i.e. richer in water than anticipated by the IAST. I plot here the activity coefficients in the adsorbed phase for CO2, red circles, and for water, blue triangles, as a function of mole fraction in the adsorbed phase. The RAST modeling for mixture adsorption equilibrium is described in detail in my previous publications in separation and purification technology. Watch also my presentations on thermodynamic non-idealities in CAF20 on my YouTube channel. In the Chemical Archives preprint of the paper by Rajendran and co-workers from the University of Alberta, transient breakthrough experimental data are provided for both adsorption and desorption cycles. My aim today is to simulate the adsorption and desorption breakthroughs with the additional objective of presenting movie animations to show the development of the gas phase concentrations as they develop along the length of the fixed bed adsorber packed with CAF20. And in addition, I also show you the developments of the loadings within the crystals of CAF20 as the loadings inside the particles change along the length of the fixed bed adsorber. The methodology for performing the transient breakthrough simulations is discussed in my papers published in Separation and Purification Technology. I also have a video presentation on transient breakthrough simulation. All the breakthrough simulation data I present are for the RAST model to describe the equilibrium between the gas phase surrounding the crystals of Calf 20 and the external surface area of the crystallites. I use the NRTL model for quantifying the activity coefficients and departures from thermodynamic non-ideality. For comparison with the experimental data published in the Rajendran paper, I show the adsorption, desorption breakthrough simulation data presented as percentage relative humidity exiting the fixed bed adsorber plotted on the y-axis as a function of a modified time parameter. The modified time parameter is Q naught, which is the flow rate of the gas mixture at the inlet with the units of cubic meters per second. T is the time in seconds divided by mass of adsorbent in kilograms. So the modified time parameter has the units of cubic meters per kilogram. I present breakthrough simulation data for 3 values of percentage relative humidity in the entering gas mixture, 25% relative humidity plotted in blue. The red lines show the simulations for 50% relative humidity, and the black lines are for 90% relative humidity. At this time, desorption starts, and the percentage relative humidity in the gas phase reduced to 0 for times approaching equilibrium. Let's look at the transient breakthrough simulations in more detail for 95% relative humidity in the entering gas mixture. The dimensionless concentrations at the exit of the fixed bed adsorber is plotted as a function of the modified time parameter on the x-axis. The red lines are for CO2 and the blue lines are for water vapor. In the adsorption phase, the component to breakthrough first is the more poorly adsorbed CO2, and water vapor breaks through last. When the bed equilibrates, this is subject to desorption, and the CO2 desorbs much more quickly than water, and the water vapor exits the fixed bed adsorber in the desorption cycle much more slowly. Let's view the development of the gas phase concentrations along the fixed bed adsorber. I plot the dimensionless length along the fixed bed adsorber on the x-axis. 0 is the entry to the fixed bed. This is the exit of the fixed bed. The y-axis is the molar concentration of the gas mixture, plotted in the units of moles per cubic meter. This is 0 moles per cubic meter, and this is 35 moles per cubic meter. Let's look at the animations. Note that the red line indicates the CO2 concentration in the gas phase, and the blue line represents the water concentration in the gas phase mixture. As these concentration fronts develop along the fixed bed adsorber. So let's start the animation. The animations are a little bit jittery due to some issues with PowerPoint, but the simulations are pretty steady. The gas phase concentration in the along the fixed bed adsorber is initially CO2. This is followed by water vapor, and the first component to desorb is CO2. If you like, you can play the videos on YouTube more than once to get a better feel for the development of gas phase concentrations along the fixed bed adsorber. The water vapor desorbs much slowly, and the desorption is still continuing, and it is just now finished. In the transient breakthrough simulations, we can also determine the averaged component loadings along the fixed bed as a function of time. The average loading is averaged over the particles and along the fixed bed. So this is the average component loadings as a function of time, and I plot the average loadings as they develop along the length of the fixed bed adsorber. The y-axis represents the molar loadings. This is 0. This is a loading of 9 moles per kilogram. The plot of the average loadings as a function of the modified time parameter is shown here. This during the adsorption cycle, the CO2 loading is indicated by the red line, and when desorption starts, the CO2 desorbs almost instantaneously, whereas the water loading is much tardier in its desorption process. So let's view the development of the loadings along the fixed bed adsorber, and I start the animation now. Red is CO2 loading in the fixed bed as it develops. The water loading is indicated in blue. The movie animations are a little jittery. This is an issue with the PowerPoint I have. And at desorption, you see that the water is desorbing much more slowly. And it is still not completely desorbed. The water loading reduces and will completely desorb at this time. So that's the animation of the adsorption desorption phase with regard to the loading in the crystal phase. Apologies for the jittery movie animations. I have no explanation why that is the case. I must sort this out within PowerPoint. But that's the end of the story.